So our task today is to discuss the weak star topology and the Banach-Alaoglu Theorem. So what's all this about? You've got some norm space over F, and then we've got the topological dual, E star, the continuous linear functionals, and as we know, that's always a Banach space using the operator norm on the functionals. But it turns out that sometimes, I've said we'll use the norm topology unless otherwise specified, but there are times when a different topology is more appropriate. For example, we've just seen that whenever you have an infinite dimensional norm space, the closed unit ball can't possibly be norm compat. We showed that last time using Ries's lemma. So that for infinite dimensional norm spaces, closed unit ball doesn't seem to be such a nice space because it's not compat. But it is compat, the closed unit ball of the dual is compat using the weak star topology. And that's the Banach-Alaoglu theorem that we're going to see in this section. So it's a different topology, it's a weaker topology. The norm topology is sometimes too strong, and sometimes the weak star topology is the one you need. And it's particularly important when we look at Banach algebra theory and the Gelfand theory there, which is what we'll be doing in the final chapter. Now, we won't be talking about topologies generated by families of seminorms in generality, but this is a typical thing you do when you're discussing topological vector spaces. You say, is your topology induced by a norm? Maybe yes, maybe no. Okay, it's not induced by a norm. Well, maybe it's induced by a seminorm, but one seminorm that isn't a norm won't give you a Hausdorff topology. But sometimes, if you combine lots of seminorms, you end up with a perfectly good topology, though it doesn't come from a norm. And the idea is that you converge, if and only if you converge with respect to every seminorm in your list. And so that gives you a nice notion of convergence, and you get a nice topology out of that, but it doesn't always come from a norm. We will briefly discuss two special cases of this, the weak topology, the weak star topology and the weak topology. We'll be focusing on the weak star topology. So let's first look at the weak star topology. And let's have a look at what is this f to the power e. This is similar to something you looked at the question sheet. So what does that mean? It's a set of all functions from e taking values in f. But of course, that's also the infinite product of copies of f, and you can give it the product topology. So you can think of that as the product over x in e of lots of copies of f. So you can think of them, or the product over x in e of, let's call it some space, let's call it y sub x, where each yx, where every yx is actually f. So it's an infinite product of the same thing. But it just means functions from E into F. But we know how to put the product topology on this. And note that E star and also E cross remember, was the algebraic dual. So E cross is a set of all linear functionals, which is, of course, functions from E into F that happen to be linear. And E star is a topological dual, which is those functions from E into F that happen to be linear and continuous. So they're certainly all subsets of F to the E. So you can take the subspace topology from the product topology. And that's the topology we're going to be looking at in this section. So the weak star topology is defined on E star, and it's a subspace topology on E star induced by the product topology on F to the E, because you just regard it as it's a subset, and F to the E is a product of copies of F. So you can give the subspace topology. But of course, that's not very informative. What you'd really like to know is what properties does it have. And, well, you may remember that the product topology is the weakest topology that makes all the coordinate projections continuous. But what are the coordinate projections on F to the E? They are the maps F goes to F of X, where X is in E. So for each X in E, you get a coordinate projection. So you can think of Px of F is equal to F of X. And that's the coordinate projection onto the X coordinate. So actually you have to think about this a tiny bit to make sure that that's still true for subspace. But if you go to a subspace, it's still true, fortunately. Little exercise. So the weak star topology on E star, that's the subspace topology that comes from the product topology, and it's still the weakest topology, but this time the weakest topology on this subset, so that these coordinate projections are still continuous. So fortunately, the sort of subspace topology from the product topology still has this, it's the weakest possible topology, so that these coordinate projections are continuous. So this topology is always called the sigma of E star E topology, and that means that's because you've got this pair of vector spaces, each one acting on the other. Anything in E star, you can evaluate it at any point of E. So if you've got a pair of elements, one in E star and one in E, each one can be sort of evaluated at the other in some sense. So when you've got a pair of vector spaces that are linked in this way, then if you use E to put a topology on E star, you've got the sigma E star E topology. So this is use the elements of E to define topology on E star. In this way, for each X in E, you've got a coordinate projection. And the other way around, the sigma E star, this is the weak topology on E. This time you use E star to define a topology on E. And that's the weakest topology on E that makes all the continuous linear functionals continuous. That sounds very strange, doesn't it? Remember, E star is defined to be those linear functionals which are continuous when you use the norm topology on E. But there may be many other topologies on E you could use that still make those functions continuous. So amongst all the topologies you can have on E that make the things in E star continuous, well, the norm topology is one, but it's usually not the weakest one. The weakest topology that still leaves those things continuous is called the weak topology. So it sounds like a bit of a tautological to say it's the topology, it's the weakest topology that makes all the continuous linear functionals continuous, until you realize that that's two different kinds of continuous. Does that make sense? Another way to think about this is NB, you can map for each x in E, we've got x hat in E star star, defined by x hat of f equals f of x. That's the standard embedding we had earlier. And that gives you a sort of connection between these two topologies, which I'll say more about in a moment. So you can regard elements of E as linear functionals on E star via this embedding as well. So they're not completely different things going on here. The things in E star give you linear functionals on E, but the things in E do give you linear functionals on E star as well via this map for each x hat. And so if you go back up here, that map here, that's x hat. So the weak star topology could also be described as the weakest topology on E star that makes all of the x hats continuous, which is very similar to this weak topology being the weakest topology that makes all of the things in E star being continuous. Any questions about what we said so far? Okay, so far it's just a topology and it's got a characterization in terms of how you can get it. But we'll be, when we want to look at the Banach-Alaoglu Theorem, we want to go back into this product space, f to the e, use Tikhonov's theorem, and get a little bit more information on which subsets really are compact in that setting. However, there are some preliminary remarks. Now, E cross, the algebraic dual, unusually, whereas E cross is not a very nice thing, it is, however, closed in the product topology. It is a closed subset of f to the e. The topological dual space need not be, and indeed usually isn't. So I'll leave this as an exercise to think about this one. I may say a bit more about that in a moment. However, a nice thing does happen. The closed unit ball of E star is a closed subset of f to the e. So although E star itself isn't usually, if you go to the closed unit ball, it is. And that's good. So that also makes it closed in E cross in the product topology. With the subspace topology from the product topology. So that's a bit of a surprise. So E cross is better here than E star is, but the closed unit ball of E star is okay. Now here's my comments on the bidual and the natural embedding. So again, I'll remind you that x hat of f is equal to f of x for f in E star. then you can look at what you get. E hat, the image of E itself under this embedding, which we now know to be an isometric linear embedding. So E hat is the set of all x hats you get to. And now, the bidual, E star star, can be given the weak star topology because it's the dual of E star. So to make it absolutely clear, then you could use the elements of E star can be used to give you a topology on E star star in just as before, just as this is the weak star topology, but it's just we're dealing with the dual of the dual space. So that's fine. And then you can give E hat the subspace topology, called the relative weak star topology. And then a nice thing happens that you might hope for, is that this standard embedding actually is weak star to relative weak star homeomorphism. So that E going to E hat, it was already an isometric linear embedding. So E hat was isometrically linearly isomorphic to E. But now, if you check through the details and just go through how these hats work, you'll find that that if you start, I'll say this, I said that wrong. You start with the weak topology on E. So that's the topology that comes from E star. So you start with the weak topology on E, and you map E into E hat, and then you put the subspace weak star topology on E hat. Then, fortunately, that turns out to be a homeomorphic embedding, which means that it's continuous in both directions. And here's a tricky, this exercise is too tricky to do yourself unless you look it up in the books. So the other exercises are all perfectly doable, but this one is harder. The fact that E hat is actually weak star dense in E double dual, and that the image of the closed unit ball of E is weak star dense in the closed unit ball of the bidual. You deduce the first, people usually prove this second one and deduce the first one from it. So this is not easy. So that's non-trivial. You have to use a geometric form of the Banach theorem, and so those interested can look up the details of that in the books. It's a fact that's worth knowing because you can make deductions from it, and I will point something out in a moment about it. Okay, so let's go back to what we really want to prove. And this is the Banach-Alaoglu theorem. The closed unit ball of infinite dimensional non-space, we saw last time, it's never compact. But it does turn out that if you're in the closed unit ball of a dual space, you are weak star compact. In the other direction, it turns out that the closed unit ball of the space itself is only ever weakly compact if the space is reflexive. Reflexive meaning that that canonical map was onto the bidual, so the space being the same as its double dual. So there's quite a difference between the weak topology and the weak star topology. But on the other hand, if you are reflexive, so that you're the same as your bidual, then the weak topology on you is the same as the weak star topology on the bidual. So it's not surprising that things work. So to prove the Banach-Alaoglu theorem, which is our main task today, we need a lemma about subsets of this product topology, where just for the moment, E will be any non-empty set, though we're really interested in it when E is a norm space. And this sort of generalizes Heine-Borel theorem based on Tikhonov's theorem. And it's, so you want some version of closed and bounded, but we know that that isn't quite right. We know there's something not quite right about that because of some of the strange things that turn out to be compact. And the choices you've got they don't look compact somehow. Yeah, they don't look bounded. So here we are with the coordinate projections that I've mentioned already. If you've got your product space, f to the e, then for each x in E, you've got a coordinate projection. Px of f is the value of the function f at x. And the product topology is the weakest topology, making all of those continuous. That's how the product topology works. So let's say that our set is pointwise bounded if each of these sets, Px of the image under a coordinate projection, is bounded. But the bounds may depend on x. So that means that it could be that in one coordinate all the values have modulus less than 1, but in a different coordinate all the moduli are less than 1,000,000, and then another coordinate, and so on. And you don't expect a global bound. So as you vary x, it may be the bound gets quite big, but still for each x there's a bound depending on x. So that's for all x in E, not x, there exists what you call a big constant, mx greater than 0, so that for all S in S, we have mod Px of S is smaller or equal to this constant depending on x. Of course, that's the same as S is a function, really, so you can say that that's modulus of S of x is smaller to mx. That's if I'm using little s. I could have used f. Would have been perfectly all right. And now, here's a characterization of the compact subsets of f to the e. Based on Tikhonov's theorem and the Heine-Borel theorem that we already know, and the fact that a continuous image of a compact set is compact. Turns out you're compact if and only if you're closed and pointwise bounded. So that's lemma 4.2. A subset of the product space is compact if and only if it's both closed and pointwise bounded. So let's prove that lemma. So let S be a subset of f to E. We prove that S is compact if and only if S is closed and pointwise bounded. Okay, let's have a look at the forward implication, because that's pretty easy. So, given that S is compact, why would we know that S has to be closed? Which theorem of topological spaces would we be quoting there? Is it always true in a topological space that a compact set must be closed? Or is it only sometimes true? Yeah, a compact subset of a Hausdorff space is closed. So I should note at this point that the product of Hausdorff spaces is Hausdorff, and F is very Hausdorff. Then, since F to the E is a Hausdorff space, which you can check, it's a product of Hausdorff spaces, and a product of Hausdorff spaces is always Hausdorff. S is a compact subset of a Hausdorff space, hence closed. That does the closed bit. What about the point-wise bounded? Point-wise bounded says, well, we have to look at Px of S. That's the image of your compact set S under the map Px, and remind me, where are these coordinate projections mapping to? Yes, they're going to F, because every coordinate has values in F. And what can you tell me about the coordinate projections in general? Let's have a... Who can tell me some important property of coordinate projections on a product space? In fact, what's the definition of the product topology? What's the single most important thing about coordinate projections when you're dealing with a product topology? Any suggestions? Continuous, exactly. Px is continuous. That's for x in E. So Px of S, that's a little p, it should be. It's a continuous image of a compact space, or continuous image of a compact set, and so it's compact. In F, but F is either R or C, so we've got the ordinary Heine-Borel theorem there. You're compact if and only if you're closed and bounded. We don't need the closed bit here. We just need to say that it's bounded. That's for each x in E, but possibly with a different bound. This shows that S is point-wise bounded. Okay, we didn't need Tikhonov theorem yet. Tikhonov theorem is for the other direction. So now, suppose that S is closed in F to the E and point-wise bounded. So then, for each x in E, there exists this positive real number mx, When I write mx greater than naught, I mean, of course, a positive real number, not plus infinity, such that for all f in S, I'll call it this time, we have modulus f of x is small equal to mx. Now, this tells you f of x is in the ball in F, centered on 0, the closed ball in the scalar field F, centered on 0, radius mx. Now, that could be a disk if it's a complex numbers, or it could be, so it could either be a closed disk if it's a complex numbers, or it could be a closed interval if it's a real numbers, but it doesn't matter, it's compact anyway by the Heine-Borel theorem. So note this latter set is compact by Heine-Borel. And now we see that S is actually a subset of the product of all of these. Well, let's think about what does that mean. We know that S is a set of functions taking values in F. But we also know that in each coordinate, the values taken are in this relevant space. So in fact, the elements of S are in here, regarding this again as a set of functions defined on E, where each coordinate takes values in the right place. So actually, S lives in here. And this is compact by Tikhonov's theorem. Well, you should think of going away and checking that the subspace topology for the product is the product topology for the subspaces, which is true. So you should make sure that the two obvious topologies you could put on this are the same, and they really are, which is good news. So this is not only compact as a product space, but it's also, well, it's the same, it gets the same topology when you regard it as a subspace of the original product and then go to the subspace topology, which is hardly surprising. It's one of these situations where you say, what else could it be? It's just unfortunate there are one or two occasions where what else could it be turns out to be something else. This is not one of those occasions. So finally, S is closed in the whole product. That also means it's closed in here as well. So since S is closed in F to the E, S is also closed in this smaller product. That works in complete generality. If you're a subset of a subspace and you're closed in the big space, you're also closed in the small space with the subspace topology. Smaller product, I'm calling it. So S is a closed subset of a compact space, and so S is compact. One or two details you might want to check in greater detail, but that's essentially it. Any questions on that proof? Okay. So we just proved lemma 4.2, and that means we can get 4.3, based on all the facts we mentioned earlier, some of which I've left to you as exercises. So the Banach-Alaoglu theorem says that the closed unit ball of the dual space E star is weak star compact. Now, we know the weak star topology is the subspace topology from the product topology on F to the E. So in fact, what you're asking here is that it's a compact set when given the product topology. It's also, so this is the same as saying that it's a compact subset of F to the E with the product topology. So we'll quote the fact that I mentioned earlier and that you're supposed to be checking, that the closed unit ball of E star is closed in F to the E. So we'll take that as read, and then the result comes from the fact that it's pointwise bounded. So let's prove 4.3. There's a proof of the Banach-Alaoglu theorem. So we already know that this is the closed unit ball in E star. So that's my notation for the closed unit ball in E star. Is closed in F to the E. But pointwise boundedness is quite easy. So we let X be in E. Then for all F in the closed unit ball and 0, 1, we have, well, definition, operator norm of F is small equal to 1. So modulus of F of X is small equal to what? This is a linear map. I would normally have used phi, but I'm using F at the moment. If F has got operator norm 1, what's the most that modulus F of X can be? Modulus of X, well, I mean, do you mean modulus? The norm of X, I would say, yes, that's right. But I knew you meant the right thing, yeah. So that means that you're at most the norm of X. Well, that's just a bound depending on X. It doesn't depend on F. So we can set mx equals norm X to give us our pointwise bound to see that the closed unit ball is pointwise bounded, and the result follows. Okay, so there is an important bit in there that I've left as an exercise, checking that the closed unit ball really is closed in the product topology. And that's quite a nice exercise, and I recommend it to you. But it would be pointless to prove that in the middle of the proof of the Banach-Alaoglu theorem. Okay, and so anyone need more time on that slide? So then the final comment is one I've made already, and I have actually given you enough facts to prove this. If you put all the facts I've told you together, we didn't prove them all, but if you look at all the facts I mentioned earlier, you could just about do this now. The closed unit ball of E is weakly compact if and only if E is reflexive, that's if and only if E hat equals E double dual. One way around is easy. If E hat is E double dual, then the closed unit ball of E is just like the closed unit ball of E double star, which is weak star compact, which means the closed unit ball of E is weakly compact. So that's how it works. But it's the other way around that's harder, and uses all that stuff about things being weak star dense and so on that you'll find mentioned earlier in the section. So you can... this is a statement you should know. But I'm not going through the proof, so it's not a bookwork proof. But you know, the more you know, the better off you are in general. Okay, and any final questions on this chapter 4? If not, we'll stop there for today.